everybody. For a couple of weeks now, I've been a proud owner of a new dm-42, which is a calculator from Swiss Micros with software based on the HP42 software from Hewlett Packard, which was launched in I think 1988. People may wonder what reason there is to buy such a thoroughly outdated calculator nowadays, and maybe I should explain that I started programming using a calculator. When I was at school, I got a Casio FX 7000G, which was the first graphics calculator, and I spent a lot of time programming that. It had a really simple language in it, a really simple Casio Basic, which I think it's called Casio Basic, with labels and go-tos and with the ability to ask questions and get input. It was a very simple language, and it was a language which a school child as I was back then could, in my spare time, without really spending much effort, could get to learn the language and program pretty much whatever I wanted, which was within the limits of the calculator. It was quite limited by memory size, if I remember correctly, something like 400 keystrokes it could store, and that was about it. Then when I started studying, I got a more powerful Casio. I got a more recent one, a 9850 or something, and I got it out of the cupboard about a year ago, and found that one of the batteries had leaked and it no longer worked. And so I thought, well, I don't actually use a calculator, but it'd be nice to have a calculator. And I searched a bit, and I got a Texas Instruments TI Inspire, and got that second hand on eBay. And yeah, I've been quite disappointed by it, mainly because I got it partly because I heard that it supported Lua as a programming language, which was a fairly modern, fairly capable programming language. And then I found that it has got two different event loops. You can write Lua code for it, which you write on your computer and then compile it, and trying to compile Lua code for it on Linux took me a while to work out how to do that. Maybe I'll make a video someday about how to do that, because it wasn't particularly easy. And I have some simple Lua programs running on it, but the Lua programs can't talk to the calculator particularly, and the calculator can't interact with the Lua programs particularly, which is a bit annoying. Well, annoying maybe is not the right word. It's a pity. It would have been nice to have access to all the calculatory stuff from the Lua programs. So I started looking for a new calculator a couple of months ago, and I found the Swiss Micros project company and their dm-42, and I thought, well, why not? And I bought one. And since then I've been doing some programming with it, and dm-42 programming is quite it's quite different. It's not like modern programming languages, if you want, and you have to think a little bit differently. And I have an example here of a dm-42 program, or an HP42 program, which is a solution to the nqueens problem. The nqueens problem, as you probably know, is you have a chessboard of a certain size. In this case, the size is 8, as signified by this number here. And you want to find a position where you can put 8 queens on the board, so that no queen can capture another one. And the more generalized problem is to say you have a board of n by n, and you want to put a certain piece, be it queens, knights, bishops, rooks, whatever, on the board, and find all possible constellations of these pieces. What's the maximum number of pieces you can put on the board so they can't take each other? Things like that. All sorts of ways you can generalize the problem. But the classical one is 8 queens, and on an 8 by 8 board. And if I was doing this in a modern programming language like Go, I'd probably start by having a function called getSolutions, which takes a, well, if we're doing this recursively, let's let it take a path. It's going to try to add a new queen to this path. It takes a path of ints, which is just a slice of ints, and let's have it take a size. Don't need a size to do that. What this one's going to do is going to return all possible paths, and there are different possibilities. So if len path, oh, am I doing this? It's been a while since I've written Go code, equals 8. Yes, it's been a while. I put that the wrong way around, didn't I? This should be like this. Sorry. I'll get back into this. Then return int of path. Get 1. Otherwise, we need to say for I is equal to 0, I is less than 8, I plus plus. Now we're going to try to work out where to put it. If safe, we're going to have a predicate called safe, and it takes a current path, and it takes I. Then we're going to say return. No, we're not going to. We're going to append. We need a list of all possible solutions here. So we have a ret int, and we're going to append to ret get solutions of append path e. We're going to have to explode that array. And we're going to capture this in ret. Okay, and at some stage we're going to return ret here. Okay, does this look okay? Maybe I've forgotten something. Let's see. Func safe. We have a path which is int, and we have a suggestion, I guess, a candidate. Candidate's a good word. For the next one, which is also an int, and it gives a boolean back. And the candidate is actually next y coordinate, isn't it? Let's call it next y, and let's say next x is equal to the length. Sorry, this isn't Go code. It's been a while. Of path. We say for next x, xy range path. Now we're just going to go through all the various things in the path. We're going to check if the queen we want to place is directly below a current queen, or if it's diagonally takeable by a current queen. So if y equals next y, return false, and if we need an absolute. Do we have a math.abs? We do. Of next x minus x equals math.abs of next y minus y. This means that it's diagonally attackable. Then we return false. And at the end, if it gets through all of them, we return true. And we have the problem that math.abs takes a float, I imagine. Yes, it takes a float. That's a problem. Okay, then let's do it differently. If diagonal, let's export this as a function then. X, y, next x, next y, return false. Let's see what happens now. Func diagonal x, y, next x, next y, bool, return x. So, yep, let's do it this way. X minus next x equals y minus next y, or x minus next x equals next y minus works okay. And what am I doing wrong here? Oh, I haven't given the type, have I? Okay, cool. So that's the basic can be caught diagonally. So there seems to be a good solution to it. Let's see. Solutions is get solutions, and we start with nil, and then we say let's just see the length, because I happen to know that the solution number of solutions for a path length of 8 is 92. So format.printf none solutions found. Len solutions. Okay, let's see how I've got this wrong. Go run main.go for 92. Okay, so this is a working solution. Let's just go through this quite simply, because it's just a simple way to work out the solution. Quite happy this one worked. So I have my starting path, which is nil. Nil is a perfectly valid value for a slice in Go. Something you have to know about Go if you don't know Go programming. I didn't want to turn this into a video on Go programming, but I do like Go programming, so I'll mention it a bit. And I'll put some timestamps down below so you can jump to the stuff where it turns into HP42 stuff. Set this path, which is a list of integers. It starts being empty, which is just nil. Nil's a perfectly valid value for a slice, because the only way you can access, you can do something with the slice is you apply it to functions. This isn't an object-oriented program in the sense that this isn't an object-oriented programming model or an object, a slice in Go, in that you can't call methods on it. For example, you have append here, which adds something to a slice. You don't say slice.add, you say append name of slice and then whatever you want to add to it, which means that it's perfectly safe. And length as well. Length is something which takes a slice as argument. And length is quite happy to take a nil as argument and return 0. And append is quite happy to take a nil as its first parameter and return something which does actually exist, or return the address of something which does actually exist. So it's quite safe to assign nil to a slice in Go. This isn't a problem. So if a path is of length 8, so which means you've already reached the end, and there's no point finding anything else to add to it, and you just return a list of paths, which is a list of integer. If not, you say I want a memory address for a list of integers, for a list of paths, and then for all possible values of where the queen can go, 0 to 8, so 0 to 7 inclusive, you check if it's safe to put a queen there. If it is, you add recursively all possible solutions of if a queen has been put in, let's say, 3 to red. And then at the end you just return the return value. And checking to see if it's safe is quite simple. That's just you check to see if it's, so the y value of a current queen. Sorry, range path, I should maybe explain what this does in Go, because it's not it's a bit unusual as Go syntax. It's also quite happy to take nil as a value of range as well. It's quite happy to take nil as a parameter, and it will just not go into a loop. What this does is it produces a pair of x and y, where x is the index, usually written as I, of course, and y is the value of this slice path. The slice of path can have values of 4, 3, 7, 8, whatever, and then x would be 0, y would be 4, x would be 1, y would be 3, etc. Just run through the list. And diagonal is fairly clear. Okay, so this is how you do it in a, let's say, modern programming language. Like Go. Let's have a look at the solution using HP42, and I will add a timestamp for this moment. It took me a long time to work out what was going on here. one thing which I found quite interesting was the usage of indirect here, IND, for addressing, for storing stuff, or for getting a value out of a register. Let's say, for people who don't know anything about HP42 code, let's get some simple stuff out of the way. Label is a place you can jump to in the program. In this case it's an A, and so if everyone wanted to jump to an A, you could do it. No one does it in this program, so maybe not. So you can start the program from outside. But let's say you put a label 04 here, and you can jump to it. You can say here by going go to 04. That will jump control of the program to 04, and it will carry on running from that point. There's another way to jump to a location in code, and that's exeq, which means execute. With exeq, the return statement takes you back to where it was called. With the goto statement, the return statement doesn't take you back to where it was called, but it exits you from the program. It's really as if this code here was just added where goto is written. Okay. Let's see. Next thing to be maybe of interest. The 8 here is really... Sorry, let's start here. Clear registers. All of the registers have been cleared. All of the registers are now at the value 0. All of the user-defined registers, I should say, now at the value 0. I'm not sure if the other registers also get modified. I'm not sure. HP42 has 99 registers. No, it has 100 registers, 0 to 99. I think a number of them are reserved for calculator stuff. Some of them cannot be written to as well. Some of them are used by other programs which are pre-installed on the calculator. For example, statistics uses some of the registers. I think somewhere around 10 to 15 or something like that are used by statistics. Okay, but the 8 here, that is the number 8. And then you tell it to store the number 8 in the register 11. So register 11 contains size. And now you have a label 00. Sorry, I should maybe explain. Up to here is the program text, and these are some notes which I made, just so I understood what was going on. Label 00, you have you recall the value of register 00, which beginning is 0 because it's been cleared. And you recall the value of register 11, which is 8. And then you check to see if they're the same number. If they are the same number, then you go to 04 and the program exits. So this 8 is really the size of the maximum value, or the size of the board size if you want. And we're expecting 00 to grow. To start at 0, or maybe start at 1. Start at 1 for good reasons which I will soon explain, and work all the way up to 8, and when it gets to 8 you exit the program. Okay, now we have an ISG00deg. This is a little bit unusual, this line. ISG means increment, and this depends upon the format of 00 of this register. This is register 00, and the increment structure, what it actually checks for is if you've got in register which you're checking on. So this thing 00 could be 05. It could actually also be a named register. HP42 supports named registers, and it looks at the number which is stored there, and the number has a structure like before the decimal point you've got the current value before the decimal point, then the decimal point, and it's got a target which is, I think, with 3 decimal places, and then it's got step, how much it should increment by each time, which is another, I don't know, 3, 4 decimal places. I think just 3, otherwise it makes no sense, or 2 decimal places. I'd have to look it up. I'm not sure. I've never actually changed the step from the... if you don't set a value for step, if it's 0, then it will just assume you mean 1. So what this does is, because register 0 only contains an integer, let's get that back. Because register 0 only contains an integer, then the target is always exceeded. As soon as you add it to 1, the target is exceeded. And the ISG works by saying, if you reach the target, no, if you don't reach the target, perform this command here. So deg is just a no-op, because this is the way ISG works. We're using ISG here just to increment the value of the register 00, and that's all we want to do with it. So if the target's reached or target isn't reached or target is exceeded or target isn't exceeded, whatever, we don't want to do anything special in that particular case. And so we put this deg here, this deg is put there really as a sort of no-op. So you can ignore deg. You can ignore deg throughout all this program. You just have to think, okay, that's a no-op. And then you store indirect 00. What gets stored indirect 00? Well, you have to go back to see what's on the stack. HP42 is a stack-based calculator. So the last thing which was put on the stack was recall 11, which is 8. So the value 8 gets stored in whatever register 00 is pointing at. And 00 has just been incremented, so 00 has the value 1 at the moment, which means the value 8, the thing stored in the thing which has just been, which is the utmost thing on the stack, the thing which has just been, the thing which is in position X on the stack, that's the utmost thing. The last thing to have been put on the stack is now stored in register 1. And we move to label 01. Here there's a number 10. As here there's a register 10. It's the first time we've had a register 10. It gets incremented. So you get to label 01. Don't worry about that. It's not important at the moment. And then the next thing you do with label 1 is you recall 00, which is of course 1 at the moment, and you store it in register 9. Okay, what's in register 9? We don't know. Let's carry on. Okay, now label 02, you decrement register 9, so it now goes down to 0. And this deg is just don't do anything don't perform any special operation if this decrement gets down to 0 or gets down below the target, because the decrement operator that assumes the number in this register, in this case 09, is in the same format. It uses the same format as the increment operator here. So the decrement operator would say if the number in 09 gets down to, so if the current value of the number 09, that before the decimal point, is the same as the target, then don't perform this. If not, do perform it or something. But we don't want it to do anything special through deg, just a no-op. Okay, you recall 09. What's it doing at the moment? It's now a 0 the first time we go through the loop, but it could be something different the next time. If x is 0, we go to 0, 0. We go to the top, we're perfectly happy, we go into the next loop. Which means 0, 0 is now 1. We've just recalled 0, 0. 11 is still 8, and 11 will always be 8. 11 is always the length, or the size of the board. Then we increment 0, 0 goes to 2, and we store indirect 8 in 2. So 8 gets stored in register 2. And now we increment 10. So there's some sort of counter going on here for how often we go through this loop. And then we recall 0 stored in 09. So now we've got the value 2 stored in 09. Now we decrement 09, so it goes to 1. Recall 09. If x equals 0, go to, I'm not sure I'm doing this correctly, what's stored in 09? Yes, that's correct. 09, if x equals 0, go to 0, 0. It's not, so we carry on. We recall indirect 0, 0. That's how it works. And this is now what 0, 0 is pointing at. So this is register 2. We're now looking at register 2. And that's where we just stored the 8 up above. We stored the indirect 0, and now we just recalled it. And we're recalling indirect 09, which is now 1. So that is the position of the queen in the first row is this, recall indirect 09, and the position of the queen in the second row is this here. We subtract it. If it's equal to 0, we go to 3. So that means if the queens are above each other, we go to 0, 3. Let's go to 0, 3 and carry on. This does a similar thing for the diagonal, by the way, but we can look at that later. Let's go to 0, 3 and carry on. We now decrement indirectly 0, 0. So the place we're putting the queen in, the place we're putting the second queen, we're now not putting it in square number 8, in row number 8. Column number 8. We're now putting it in column number 7, and we're going back to 0, 1. And we increment our 10. So the 10 is some sort of counter for how often we're going through the loop. We recall 0, 0, store in 0, 9. Yep, so that's 2 is going to 0, 9. So that's the current row is being put into 0, 9. And then we decrement it. So we now go down to 1 again. And we check. If is equal to 0, go to 0, 0. No, this is the first time we're checking it for this new position of the queen in the second row. So in column 7. We indirect 0, 0, we call indirect 0, 9, so this will be an 8 here. That's where we put the first queen. This is now a 7 where we put the second queen. X equals 0, go to new 3. No, it's not 0, we carry on. And now we get the diagonal check. We do an absolute of this 8 and 7. So that's now going to be a 1. These are the last values which we have on the stack. So the value in the Y position on the stack is an 8. The value in the X position on the stack, we subtracted it. There's a 1 on the stack. So 1, then we recall 0, 0, recall 0, 9. We subtract, and that's the that's the row. That's the row which we're currently checking with. And at the moment, that's the highest row which is safe, so which is row 1. So that's the one with the queen in position 8. So we call 0, 9. That's the queen in position 7. We subtract and there's 1. And we check if they're different. If they are different, we go to 0, 2. And we start. And now we try this moment. This is going to be x of 0. So we're now checking the new queen we want to put in row 2 against the queen in row 0. There is no row 0. So we go to 0, 0. We go to the next loop. And that's how this is built up, basically. And what this does here, as label 0, 3, is this goes through the possible, this checks all possible positions. So what this will do is the first line, we've had this once, this takes our guess of where to put the next queen and moves it to the left. So it checks, okay, position 8, is there a problem putting a queen in column 8? Yes, there is. Then let's try it in column 7. It's a problem putting queen in column 7. Yes, there is. And try column 6. And it carries on. And either it finds a safe place to put the queen by going through this 0, 1, 0, 2 loop, or if it doesn't, it will decrement the current position we're working with. So rather than finding a place to put, let's say, the 5th queen, if it can't find a place to put the 5th queen, it will go back to where it put the 4th queen and will try to find another place to put the 4th queen. And then when it finds another place for the 4th queen, it will get back into the loop and it'll try to find a place to put the 5th queen. And if it can't find a place to put the 5th queen, it'll go back and try to find another place to put the 4th queen. Let's say it now can't find another place to put the 4th queen, then it will try to find another place to put the 3rd queen, and then carry on going out. So this is a backtracking algorithm which is going on here. Which is somewhat different to the way the Go code works. The Go code just checks all possible solutions. This is not Go code isn't a backtracking algorithm. Okay. Let's try to make this a little bit more modern. And one way to make this more understandable is to just put some names to things. So if we say that register 11 is maximum, then register 00 is the current place we're looking. And you can regard registers 1 to 8 inclusive as being some sort of list, some sort of array with the positions which you will later want to look at. We are using register 00 as a way to index this array, index into the array. I've called it current here, we call it index, and this places array here is registers 1 to 8 inclusive. So if current, the one we're looking for, one we are now filling, is equal to max, we return R10. R10 is the number of guesses, or the number of loops, something like that. Not sure exactly what to call R10 at the moment. So when we exit this program, the result for where the queens are going to be are in registers R1 to R8 inclusive. Okay, then we have here, I think we got quite close to explaining this. Places current, sorry, the label 03 is called if places current equals places R09, so this is not safe. So if a queen which has already been placed is above the queen we want to place, R09 is sort of like guess, if you want, suggestion, candidate. Let's call it candidate. Do this. Okay. Good. Now you can sort of see what's going on there. We have here if place is current. So if the current this is a loop we're going through to make sure that everything works. If place is current is above places candidate, then it doesn't work. And we go to label 03. And we go back. Oh no, I've done something wrong here, haven't I? I'm gonna have to think about what I did wrong here. Let's take this back. You see, I get quite confused trying to work out what's going on here. R9 is not current. R9 is the past position, isn't it? So if R9, the past position of the queen, clashes, a past position of the queen clashes with current, then we go here and we try a new current position. If it doesn't clash with current, and let's say this one doesn't go wrong either, then we go to label 02 and we try the next oldest position of the queen. So we're gradually going up the queen positions, which we've already saved. That's it, yes. So R09 is certainly not candidate. That's totally the wrong word for it. Current is candidate. Candidate row, current row we're trying to, and R09 is an old row, one of the older rows, one of the older row numbers. So this is a loop from the current row number -1 down to 0 is what we're doing here. But it's all quite complicated because you've got labels jumping here and labels jumping back, and it's quite difficult to write this in using just ifs or using for loops without using goto. Okay, maybe I'll stop now because I think I can show you it working, of course. Where is it? I programmed it into the calculator. So if I go to program, you can see it. I named it NQ. I named it NQ so I can find it rather than calling it A. I programmed all this into the calculator here. One thing I should maybe show you, because it took me a while to work out, is how to enter indirect addressing. Let's get out of this, and you enter indirect addressing by clicking store, then you press the dot button. You can press indirect here. And that will now store 0 into, let's make it a number which we can certainly check, and store indirect in register 2. So that should store 15 in register 2, and I recall register 2, oh no, of course it won't. It stores it indirect to whatever the value of register 2 is. So if I recall register 2 again, that's 4. So that's 15 store indirect register 2, and that will now store 15 in register 4. That's how it works, isn't it? Yes, good. Okay, let's just let the program run, nq, and it works for a while. It comes up with a number 876. So it seems to, so this line here with increment, let's put that on top. This line here with increment 10 has been called 876 times. So that works really quite quickly. And if we want to, we can now recall the positions we have. So 01 is 8. Let's just write these down here so we have them. We have position 8. Recall 02. There may be a way to recall these quicker. 4. Recall 03. I'm not sure how to recall many at one time. 1. Recall, where were we? This was 1, 2, 3, 4. We're now at 4 is 3. Recall 05 is 6. And recall 06 is 2. Recall 07 is 7. And recall 08, and now we have all the positions, which is 5. And that was the solution it found, the first solution it found, but the only one, because it stops as soon as it finds the solution. And you can sort of imagine, if you think about this for a while, about what this looks like on a chessboard, that this is a safe position. Let's see if we can find this in the Go code. Let's print all of these solutions for solution range solutions format dot print ln solution. Okay, let's see if we can find this. What I do, I had here, down here, I had a shell, didn't I? And we're looking to find, oops, what did I do? I didn't save it. Okay. What we're looking for is, get back up to 1, because we're 0 indexed here, we're looking for something which starts with an 830. And it's actually the last solution it found, which makes sense. It was the last solution it found, because in the Go code we started, difference with A code, we started with I0, I less than 8, and in the HP42 code we started with if places current equals max. So we started with 8, 7, 6, 5. We went in that direction with this. Here we were decrementing places current and not incrementing it, starting from 0. And in the Go code we started with 0, and then here it is, started with 0, and we incremented it to 8. So we just did the other way around. Cool. I hope this has been somewhat interesting. And yep, maybe I'll do some more HP42 or plus 42 videos at some stage. Many thanks.